Welcome back. The agenda for today is integers. An integer is commonly represented as a group of bits in computers. A bit is a single value with two states. For example, bit can be 0 or 1, on or off, or even false or true. Now a collection of 8 bits is known as a byte, and a collection of bits again can represent different things. For example, 101 can represent a number. It can be also color, sound, letter, book, or a person. So depending on the context, a collection of bits can represent different things. Now let's see how numbers are defined within a computer program. A number is defined as an ordered collection of bits. And the three most common ways of representing numbers in a computer program is base 10 or the decimal number system, base 2 or binary representation, base 8 or the hexadecimal number system. Now in base 10, there are 10 digits, 0 to 9, and each digit of a number can have an integer value ranging from 0 to 9. So 138 in base 10 is 100, 3 tenths, and 8 ones. Or equivalently, it is 1 times 100 plus 3 times 10 plus 8 times 1. Now notice the first column is 1, second column is 10 times 1, the third column is 10 times 10, which is 100. So each column is 10 times bigger than the previous column. Now similarly, base 2 has two digits, 0 and 1, and each column is 2 times bigger than the previous column. So 10101 in base 2 is 1 times 16 plus 0 times 8 plus 1 times 4 plus 0 times 2 plus 1 times 1, which is equal to 21. So again, the first column is 1, second column is 2 times 1, third column is 2 times 2, fourth column is 4 times 2, the last column is 8 times 2. So each column is 2 times bigger than the previous one. Finally, base n has n digits. So 0 to n minus 1 are the n possible digits, and each column is n times bigger than the previous column. So base 8 is hexadecimal, so it has 8 digits, 0 to 7, and each column is 8 times bigger than the previous column. Now when we switch to Visual Studio, we will see why it's important to understand how a number can be represented in each of these three different ways. Sometimes it's easier to represent numbers in decimal, and other times it could be easier to represent numbers in hexadecimal system. Next, let's see how to represent negative integers in a computer program. Negative numbers are encoded using 2's complement representation. So what's a 2's complement representation? A 2's complement of a number can be obtained using what's known as 1's complement. So let's see what a 2's complement is through an example. So suppose a is a 4-bit integer, 4-bit matters. A is equal to 5. The question is, what is minus a? So let's see first how a is defined in binary or base 2. So a in base 2 is 0101. We need this binary representation to convert it into 2's complement representation. So 2's complement of a number is 1's complement of a number plus 1. So now what's 1's complement of a number? 1's complement of a is obtained by flipping zeros and ones in the binary representation of a. So again, if we flip all zeros and ones in 0101, we will get the 1's complement of a, and if we add 1 to that, we will get the 2's complement of a. So 1's complement of 0101 is 1010, and 2's complement of a is 1010 plus 1, which is equal to 1011. So minus 5 in computers is represented using 1011. So what's key to remember is negative numbers are encoded using 2's complement representation. And 2's complement of a number is obtained by first taking 1's complement of the number and adding 1 to it. Now we'll see what are the different types of representing integers in a C++ program. The first type is a signed int. A signed int is used to represent both positive and negative numbers. The size of a signed int is 4 bytes or 32 bits. So its range is from minus 2 to the power of 31 to 2 to the power of 31 minus 1. While an unsigned int only represents positive numbers, so its size is 4 bytes or 32 bits again, and its range is 0 to 2 to the power of 32 minus 1. Now let's switch to Visual Studio and let's look at some examples on how to represent integers in decimal, hexadecimal, and binary format. We will also see examples of declaring integers, positive and negative integers, and we will see how 2's complement encoding works within C++. So first, let's see examples of defining an integer with a decimal number system. Here, int a is equal to 11. 11 is in decimal or base 10. So it is 10 times 1 plus 1, which is equal to 11. And in the next line, we are we are assigning a binary representation. So 0b1011 is a binary literal. 0b is a prefix, which tells the compiler that the number is in binary format. 1011 is equivalent to 11 in binary. So 1 times 8 plus 0 times 4 plus 1 times 2 plus 1 times 1, which is equal to 11, which means 1011 is the binary equivalent of 11. Now the question is, once we assign a to be equal to 0b1011, and when we print out the value of a, do we see the binary representation of 11, or do we see the decimal representation of 11? So let's confirm which is the representation that we will see when we print by executing the code. So let's continue the execution and we should see a print statement. The print shows that the number is converted back to decimal. Even though we assign a binary literal in line 12, it is converted back to decimal and we see 11 as the output. Now, if we want to actually print the binary equivalent, we can use a special template within C++. So including a file called bitset, let's just use a template called std_bitset. For now, don't worry what templates are. We will go through templates in more detail in later videos. For now, templates are functions which can be called with some parameters. Here, the parameter says how many bits of an integer we want to print. So std_bitset 8 parenthesis a says that we want to print the integer a in binary format, and we want to print only the 8 least significant bits. We've seen that an integer has 32 bits, so we're only printing the 8 least significant bits. So let's continue the program. Okay, now notice a in binary is 00001011. So we can change this and we can print all 32 bits by providing 32 here as parameter for std_bitset. And let's run the program again. Now we should see the 32-bit representation of this integer, wherein most of the significant digits are all zeros. Only the last 4 digits have a value. So 1011 is the value of 11 in binary. Now let's see how to represent an integer using hexadecimal number in C++ program. To do that, you prefix it with 0x followed by the hexadecimal number. So 0b again is equivalent to 11 in hexadecimal, and 0x 0b is a hexadecimal literal. So when we make this assignment, we want to check again when we print a whether the hexadecimal number will be printed, or again will it be converted to decimal, and do we see the decimal number in the output. So let's continue running the program. Okay, now notice again 0x0b, which is what we assigned to a. However, we see the print value of a to be equal to 11. So no matter what we do, we assign a binary or hexadecimal, C++ converts it back to decimal and then prints out it as a decimal number. Now we will see why it is important to represent a number using binary, hexadecimal, and decimal shortly.